Our next speaker is Takanobu Taira, also from City University London, and he's going to talk about complex BPS soliton with real energies. So after 10 minutes, when you have 5 minutes remaining, I will let you know, Taka. So please
Okay.
go ahead.
Okay, thank you, Francisco, and organizers for allowing me to speak in this meeting. Today, I want to talk about a work I've done with my supervisor, and it is based on these two papers. Okay, so here's the plan for my talk. I will begin by motivating what's called a PT symmetric theory, and then I'll give two examples. First one is Toft polyacryl monopole, and the second one is sine Gordon soliton. And I'll talk about the non-Hermitian extension of these two examples. So the motivation. So the PT symmetric theory is a theory which has a non-Hermitian Hamiltonian, and this is different from an open system because the probability is preserved over time, and the time evolution is unitary. So this is really a closed system. And this was kick-started by this paper, and this figure is taken from this paper. So what this is the energy spectrum of this complex Hamiltonian that's circled in red. Now, if n is bigger than 2, you can see that energy spectrum is real, and it's bounded from below. When n is smaller than 2, some of the pairs of energies coalesce, and they become complex conjugate pairs afterwards. And this point is called exceptional points. Another motivation for PT symmetry, it's success in classical optics. So in classical optics, there's something called the Helmholtz equation. And this is equivalent to the Schrödinger equation at the level of differential equation. So what you can do is you can use the technique you obtain in PT quantum mechanics and you apply it to a classical optics. And they performed numerous experiments, and it was quite successful. And it was successful enough to be nominated apparently for the top 10 physics discoveries. This was published in 2015, Nature Physics. So this is all nice, but why is this complex Hamiltonian real? I mean, why is the energy real? And you may already guess why, but it's the PT symmetry. So the question is PT symmetry responsible for the real energy? And to answer this question, you start with the PT symmetric Hamiltonian with the eigensystem, and you have a PT symmetric eigenvectors up to phase. Now, you can follow this logic and notice the eigenvalue is actually real. Maybe I'll explain this bit. Here I use the fact that PT symmetry is the antilinear operator, so any parameter in front will get complex conjugated when it passes through. So you can see the eigenvalue is real. So now the answer to this question is actually no. And the reason for that is because these two conditions doesn't always come together. And this is quite important, and it has different names. So when these conditions are satisfied, you say your H has PT symmetry, and you can see the eigenvalue is real. When one of the conditions is broken, then you say PT is spontaneously broken. In this case, eigenvalue comes as a complex conjugate pairs. And when both of these are broken, you say PT is broken and the eigenvalue is complex. It doesn't come as a conjugate pair. So the main message here is that it's not enough to have PT symmetric Hamiltonian. You also need PT symmetric eigenvectors. And we'll see a similar behavior in section 3 when we talk about sine Gordon soliton. So instead of having eigenvectors here, we're going to have solitons here. And the question, so this is all nice, but the question is, can you realize the physical theory out of this non-Hermitian Hamiltonian? And the answer is yes. And so to realize the physical theory, you need what's called a Dyson map. And I'll just explain the surface level introduction. If you're interested, I would recommend reading this book. But the point is that you have a PT symmetric Hamiltonian. And if you manage to solve this algebraic equation where P is the parity operator, then you can find the Hermitian operator Q, which maps the non-Hermitian H to a Hermitian little h. And notice that this equation depends on H. That means Q depends on H, and that means Q depends on theory. And also, it's not unique, the solution. So you might wonder what's the point of finding Q, because big H and little h are isospectral because this is a similarity transformation. And the point is that you need Q to define a physical observable and a positive definite inner product. And this is explained well in this paper if you're interested. But the very basic idea is that if you have a non-Hermitian operator that you're interested in, for example, position operator, then you choose an initial assumption. So you assume this as an initial assumption that your big H is mapped to a little h, which is Hermitian. Then with this assumption, you can fix your Q to be unique. So before it wasn't unique, now it's unique. And obviously, if you change X to different operators that you're interested in, you get different Qs. So this is one reason why you need to find your Q. Another reason is that your physical theory, you want a probabilistic interpretation. And for that, you need a positive norm. And if you just stick to the Dirac inner product, your norm can be negative, so it's not positive definite. So what you need to do is you need to define a new inner product. And it turns out that you actually need to use Q to define the inner product. So since Q is theory dependent, you notice the inner product for this non-Hermitian theory is theory dependent as well. So this was the quick introduction. So here's some example. I've taken this example from this paper, but basically this is a Sine-Gordon theory with extra complex term, and they use this Dyson map to show that this is isospectral to this usual Sine-Gordon theory. And in section 3, what I will do is I will look at the solitonic structure of this theory. But first, I will talk a little bit about Toft-Polyakov monopole. And just to let you know that I'll be using this standard notation. So I'll be using this Dyson map and denoting it as eta. Okay, so now the monopole. Since I don't have much time, I won't explain the details. I'll just tell you the ideas. But basically, the standard procedure to find the Toft-Polyakov monopole is you start with the action and you choose answers. You insert your answers into the equations of motion, and you find the set of differential equations which you can't solve, but you can solve it by taking what's called a fourfold scaling limit, or I think more commonly known as BPS limit, and you find the set of solutions. So I have done that for this particular action. So this action is complex. It's non-Hermitian. Now, this solution has some freedom that one needs to fix. And to do that, you put a boundary condition to fix the freedom. And the condition that I want is I want this solution to have finite energy. And this is equivalent to requiring that my solution converge to a vacuum solution in the spatial infinity. This is called the Deriv's scaling argument. But our solution is real. So it can't possibly converge to a complex. So the vacuum of this action is complex. So it can't possibly converge to a complex vacuum in the spatial infinity. So this seems like the end of the line. And to resolve this issue, what we do is we perform a similarity transformation. I have taken the Dyson map from this paper, a slight modification of it. And what you should notice, if I go back and forth between first and second slide, notice that this solution doesn't change. Sorry, this solution doesn't change. However, this complex vacuum now becomes a real vacuum. But since the solution doesn't change, this Derek's scaling argument, this assumption works perfectly. So you can fix your solution with this well-defined boundary condition. So now you find the finite energy. And so I was planning to explain each step of how to evaluate the energy, but since I don't have much time, I'll skip and just show you the energy. So this is the energy. So now you can see it's finite, and you can see it's real. And now that we know energy is finite, I will explain why it's real. And to explain why it's real, it's better to look at much simpler model. So I'll look at the Sine-Gordon model.
5 minutes, Taka.
Okay, thank you. Okay, so here's the model. I've taken this model from this paper. So this is just a standard Sine-Gordon theory with the extra complex part. And you can use the Dyson map calculated in this paper, and the corresponding Hermitian potential is just the standard Sine-Gordon potential. And because it's just the standard Sine-Gordon potential, solution is just the standard kink solutions and anti-kink. And you have 4 solutions because you have plus minus in front and plus minus in the exponent. Now, let's assume that we don't know that this paper exists. And we were left to find the solution from this potential instead of this real potential. Then it is possible. It's a little bit harder. Actually, it's much harder. But you can still find the solution. And it turns out that even though after all this hard work, all you find is that it's just a shift of the real solution. Okay, so these are the solutions. Now the energies of these 4 solutions are finite and real if epsilon is smaller than 1. And now let me explain why it's real. So this is our potential. And this potential have a PT symmetry. And it is a symmetry because you're integrating from minus infinity to plus infinity for x. And this is PT symmetry if you assume your sort of fields to be pseudoscalar. Now, let me complex conjugate this potential like this. And then let me pour minus into sine and cosine like this. Now notice that if our solution satisfies this kind of relation, then this part just becomes phi. So this is equal to V. So that means V conjugate is equal to V. So that means energy is real. And this is kind of reminiscent of how I explained at the beginning that individual eigenvectors needed to be PT symmetric. Here it's like saying individual soliton solutions needs to be PT symmetric. However, this isn't quite true because if you look at the explicit form of the solution, if you perform this transformation, all that changes is that this sign flips and this sign flips. So that means PT transformation of this solution doesn't give it back itself. It gives different solution. So this looks bad. But actually, you can utilize the fact that all 4 solutions share same energy. So although PT transformation maps solution to a different solution, since all solutions share same energy, it doesn't really matter. You can still argue that energy is real. So the point here, the main message of my talk, is that in the eigenvalue problem, you required individual eigenvectors to be PT symmetric. In the soliton case, we found that we require pairs of solutions to be related by PT symmetry. So you can't just find one solid solution and be happy with it. You have to find the PT cousin of its solution. Okay, that's the end of my talk. I just wanted to compensate the lack of pictures in my talk with some pictures. This is a different model, actually. This isn't a sine Gordon. This is a kink solution, but maybe I don't have time to explain, so I'll just skip. So here's the conclusion. So you can still study non-Hermitian Hamiltonian if you find the correct similarity transformation. Similarity transformation is not just a mathematical exercise, because you need that to find the physical observable, and you need that to define a correct inner product. Finally, the reality of the soliton energy is guaranteed by the symmetry between the solutions, not individual solutions. And the future work would to study a more Dyson map. And I didn't really explain in detail what exceptional point is, but yeah. So that's the end of my talk. Thank you for listening.
Thank you very much, Taka. Let's send Taka. Thank you very much. We have 5 minutes for questions. So there is a question from Michael. Please, Michael, go
Thank you,
ahead.
Francisco. My question is, we know that in many field theories, soliton solutions or kink, when we have soliton solutions or kink solutions, there are some differential operators which control the stability of the corresponding solutions. For example, in the case of 5,4, it is well known that the stability of kink solutions is controlled by the Hamiltonian operator of reflection of special Taylor quantum system. So my question is, what did you try to see what are the differential operators which control the stability of your soliton solutions?
So unfortunately, I didn't study the stability of the kink solution. So I won't be able to maybe answer your question.
Okay, thank you.
Sorry. Yeah.
Can I intervene in this point because this is related to this question? Sorry, I don't want to take. Yeah, if your soliton is a magnetic monopole, because I understand from your research you have also done that, the stability will come from the charge quantization condition. Am I right? The Dirac quantization condition, which is valid. So that might solve that problem in that particular case, but it's not clear to me what you have. That was actually my answer to Mikhail's question on the stability. I don't know. Is that because you would have topological stability in that case if you have magnetic monopoles? Am I right in my understanding, or?
So I'm not sure if I fully understand the question, but if the question is if there's a topological charge for my magnetic monopole.
Yes, that's the question. Because if there is topological stability. So that answers Mikhail's question for this particular soliton. That's all I was saying. So is there any such a condition, or which I expect it would?
Yes, topological charge. I think it corresponds to the winding number of the, because our magnetic monopole is very similar to standard magnetic monopole.
Precisely.
It doesn't differ too much, and if you calculate the topological charge, it gives you the winding number of the solution, which is constant. So I suppose maybe that implies a stability.
For sure, if you topological stability, you cannot. That would, but that's only this particular soliton. In general, of course.
Yeah.
I agree. Very nice talk, by the way, and very nice work.
Thank
you. Thank you. If I made a quick comment, so I think that also the question of Mikhail maybe is related with the fact that when you take this, the soliton, the one kink solution of the sine Gordon, and you study stability, you get to the complex real reflectionist potential. So I think that naturally, maybe he's wondering if now they will get some extended PT extended version of such a potential. So this is, but maybe it's not very difficult to check what it is there. So But of course, I don't have an answer to that. But, I don't know if there are more questions. We have time for more questions.
Actually, I have just a naive question.
Yes, go ahead.
The petit symmetry is always a mapping from, let us say, a complex Hamiltonian to a real Hamiltonian. So, in other words, there is always some kind of similarity transformation that connected to, or not in general.
So is the question, can you always find the similarity transformation?
That's right.
Okay. So to find the similarity transformation is to solve this equation, and it's generally really difficult to solve this equation even for simple model. So I don't know if there's a regular proof, but I don't think you can find it for any model.
Maybe I can comment on the classic example in quantum mechanics, Ix to the power 3. The similarity transformation is only known perturbatively, so there isn't even a closed formula for that simple example. Okay. But you need it in order to define your observables. So that's essential. So we have seen some previous talks where people analyze directly the non-emission model, and I wonder how this is justified and what are the observables. So that might be a question for Alex and for Nick. Yeah. If you don't have the similarity transformation, which I think in your models you didn't have, how do you define the physics?
Yes, there is an extra question from Taka.
We can discuss the open session, I guess.
Okay.
Yes, there is a question. There is an extra question from Taka from Luis. Please.
Hi, thank you very much for your talk. I have a question. In quantum field theory, you have this thing that it is called Cyber-Witten theory, where you take a supersymmetric Young-Mills theory and you produce, by Wilson randomization, you produce an object that can be studied by using something that is called Cyber-Witten data. In this procedure, you can identify something like Tikhov-Polakov monopoles and so on. So I can speculate that in this case of petit-symmetric theories, you may have something like that. Do you know if someone is studying around that as petit-symmetric extension of Cyber-Witten formalism?
Not to my knowledge. PT-symmetric field theory itself is quite new, and I personally don't know a paper which studies PT-symmetry extension of Cyber-Witten model.
But if you have a solution of the Hoff monopole, one can really speculate that there must be something about that.
If I may add a word, why are you so focused on the Cyber-Witten in particular? You have monopoles all over the place. I mean, in grand unification models, why the Cyber-Witten in particular, which is just a sort of a standard field theory in a supersymmetric fashion, after all.
Because there is a connection between Cyber-Witten and integrable models. So I think there may be, and integrable models can be extendable to petit-symmetric systems. So maybe there is a connection between petit-symmetric systems, Cyber-Witten theory, and the petit-symmetric monopole.
So it's the BPS structure that drives your attention. Yeah. Because there are many also in that case there are many other examples. I mean, I was just wondering why Cyber-Witten in particular.
Yeah,
which is a wonderful theory, because which is, yeah, as you say, it's an example of an exact solution in field theory in n equal 4. Okay.